Good morning. Time to get after it. Today, we'll be talking about arrays and container classes. So we've got a nice cover shot here of two ancient technologies, one of which is a data punch card, which is how they used to program computers. The other ancient technology, of course, is a thumb drive. We used to use those things back in the day. Okay, so we're going to talk about arrays as they show up for us in C and C++. We'll start out by understanding and looking at how we're going to use them. So it's very important, these things in red here, you need to understand the way that C arrays work, including multidimensional arrays. We have to understand how pointers work, including function pointers, which were always a super hairy subject for me in C. It's very nice that we have function objects now with the way that the STL works in C++. Function objects, huge improvement. But having a fundamental understanding of what function objects are doing for you, the work that they're replacing, what function pointers actually need and how that works is important to understand in terms of the guts of what's going on there. I have this set on Do Not Disturb. It's Dr. P here. Okay. Got no video. Got it. How does that happen? Pow! How about that? Great call. All right. Sorry about that. No, it's Dr. P. We're good. All right, we're ready to go here. All right, so what I said still stands. Those of you who are wondering, there's our ancient technology photos. Check that out there. And then back to here, it's important to understand how strings work. They were always kind of a magical thing because in reality, they're just a pointer to some memory and then an agreement on the way that string functions work. So string functions always take some base address and then they keep going until they see a null terminator. So that was what was fundamentally important about strings, C strings, which is really just a bunch of characters in a row, a bunch of characters all strung together, if you will, and that's why they were called strings. So those strings are just a bunch of characters and we have some place to start at them, and then our functions that do measurement or copying or searching, they all just continue to look at characters one at a time until they find that one character that's the actual 0 byte, that's the null terminator, the true value of 0. When it sees all zeros in 8 bits, then it shuts the function down, whether that's counting the length of it or what have you. So all of these things are really good pointers, arrays, and strings from the C level. It's easy to make the code examples, and the slides have that stuff because when you understand what's going on at the C level, it is really straightforward. A lot of stuff gets sort of occluded when you have objects wrapped around it from C++, so there's kind of a little bit of magic that goes on there. So that's why most of our slides and stuff are done more C style when we can, because it shows you exactly what's going on there. You might have to also do this depending on where you go. You might have to show up with some legacy code and do some stuff in C, or early C++ written style so that it's still very much C-like. And you might see some in interviews. But as we start working here in 281, obviously we keep pushing you towards the STL, pushing you towards using the C++ constructs that really do save you time and code and energy and debugging and frustration. There's just almost all savings when we're using this stuff. So we're going to avoid using C arrays. Instead, we're going to use vectors. Vector templates are great for us. They give us dynamic memory. That's important to remember. A vector is 3 pointers in the local scope. The rest of the memory is dynamic. So you may get dynamic memory errors and you say, well, I haven't declared any memory. But if you use a vector, vector declares dynamic memory on the heap for you. And when the vector goes out of scope, it gets rid of the memory on the heap. It deallocates those bytes that you have stored. So be aware that that is dynamic memory. Avoid pointers whenever possible. There's nothing wrong with pointers, but they are a source of a lot of errors. When we start thinking about things indirectly, we're not as good. We're all much better at thinking directly than we are thinking indirectly. So when we start using pointers, we start talking about doing things indirectly, and that's where people often get led into problems. So we're going to avoid using them wherever possible. However, this project 2 just coming up, we've got some pointer work to do in the pairing heap portion of writing your own priority queues. So be aware you will be working with some pointers here, and you just have to be careful. You have to be very careful. You have to be pedantic. You have to make sure that every pointer goes exactly where you know that it's supposed to go. And every time you make any kind of updates, you have to make sure that all the pointers are good. We are going to, of course, use C++ string objects. That's going to make our lives a lot easier as well, because they're just like vectors. In reality, a C++ string object is very much like a vector. It's got that same sort of base pointer and then some memory, and it goes at it. But it's also got some trickiness in there. For speed, they've made the C++ string 32 bytes, no matter what's in it. Even an empty string takes up 32 bytes. But that allows it to hold some pointers internally. It also allows it to hold some memory internally. So for short strings, strings that are less than 16 characters, instead of that memory being on the heap, it is right there locally. So that's what gets you a lot of speed. Later on, if you need more space, the string automatically finds space on the heap for it and uses the pointers inside of the string object to point to the heap instead of pointing inside of itself right there on the stack. So it's a really brilliant thing that's been built there. And for 99.99% of us and 99.99% of the time, we just use it and let it be. And so that's good. So it's nice to understand it because it does do work for you, but we're also very happy not to have to implement it. So that's what's going on. Here's a fun slide. Look at what this code does. In line 5, we've got this cout of I square brackets A end line. Then if we go back up to line 1, we see that A is just an array of doubles, and we see that I is an integer. So line 4 makes a lot of sense. We can access an array A at some integer index. But what's going on with line 5? Is that legal? Is it a compiler error? Does it give us a runtime error? What's going on there? It's I square brackets A, so it's the integer with square brackets at the array index location. This one is pretty tricky. It turns out that what we have is something known as syntactic sugar. Square brackets is syntactic sugar. Square brackets allows us to do some array access. And what it converts to is like this. Here we see A square brackets I converts to A, which is the base address of the array, plus I, which is how far away we have to go. These A size things, so whatever we have there. So if I look at A as a pointer to double, if I then plus I to it, where I is some integer, it's going to move over that many doubles, which is fine when I'm looking in an array because those doubles are all right next to each other. So I take that base pointer, offset it by the index that I want to look at, and then dereference. So that's where we take the base pointer and the offset, put that in parentheses so the addition happens first, and then the dereference says, get me what's at that pointer. So A square brackets I converts to dereference of the quantity A plus I, whereas I square brackets A converts to dereference of the quantity I plus A, which is the same as A plus I because of the commutative property addition. So these two things work out equivalently. So this is really crazy. And obviously, we hope that you never program like this. This is just a great way to confuse everyone else that's working with you, including yourself, 20 minutes after you've got this figured out and then stop thinking about it. You come back and look at it and you try to remember, what was I doing again? That doesn't work. Doesn't work. Plus, you know, it's very dangerous in the sense of if I gets to be too large or A gets to be too large, then you pretty easily jump off the end of this thing. There's some of the values in there. So be aware that this is not a great way to do things, but it's about a fundamental understanding of what's going on here. That's why this slide is in there. These two expressions are equal as written. Some more review on arrays in C and C++. We'll start out here with a character array in line 1. That's A. And you see when you declare that with just square brackets and nothing inside there, the compiler is going to give you just enough room to fit the things in the literal that you have on the right-hand side of the equal sign there. So that character A array is going to be filled with those 4 characters. So what you don't want to do is try to use A as if it were a string. Because in a real string, we need to have that last character be a null terminator, a 0. So I need to make sure that if I'm going to use A as a string, which I could do if I was guaranteed to have a null character there, then I could use that A as a string, or I could use it as A square brackets and access those things using the syntactic sugar of square brackets. So syntactic sugar is called that because it makes it really sweet. It makes it easy to write. That's why we call it syntactic sugar. It still does something fundamentally multiplication and addition there with the dereferencing, but we just write it with the square brackets here and we feel great about it. So what would be in A would technically be this string EECS, but I can't print it or do any string operations on there because I am not guaranteed that the thing that follows the S is a null character. Sometimes it will be, sometimes it won't be. If it's not, any string function is going to try to keep reading past the S as if that next thing were a letter. And it will invariably try to print those things out, and you'll start to see garbage looking output. Excuse me. But square brackets, A, square brackets 0, so we say A at 0, A of 0, a couple of different ways you say that. We've got A square bracket 0. It's changing that first character to a capital E. So now we've got EECS in there, and you can see a picture of that on the far side. That's kind of what we've got going on there with some array indicators and arrows pointing to what they're actually pointing to in data. If we go and access that square brackets to read out of, here we can assign this character C the value that's in A at index 2, which is of course 0, 1, 2. That's the C in the character. So now the character C contains a capital C. I can take something like a character pointer P and declare that and also set it equal to A. So we saw that we declared A up here as an array of characters, but I can also set a pointer to character equal to A because A is really just a pointer. Down here we can set that pointer equal to something in the middle of that array there. We said let's go to index 1. That's going to give me a character, and then if I put the address on there, that's going to give me the pointer that is that second E. We like arrays because they give us random access and constant time. I can get to any point in there, just square brackets, do the thing, or take that base pointer, add a value, and dereference. I can get there in constant time. Index always starts at 0 because really that 0 is the offset. How far away from A am I going to be? Well, if A is where things start, A plus 0 is where I expect to see the first thing, which is why we have 0 indexing. The size of the array has to be separately stored, so you can see that with just this declaration here, there's no concept of a place for the size. If I wanted to keep track of that, so I was going to do some other things so that I could look in A to write maybe a count control loop, for loop, so that I wouldn't go off the end of it, I would have to know that the size of that was 4. I wouldn't have any way to look at that pointer and inherently know that there was only 4 characters there. I would have to use some separate storage of the size. There's no bounds checking. I can go right off the end of this, no problem. I can say A square brackets 10, and it's just gonna start at that A base address, add 10 bytes, and then dereference what's there. If that's your memory, you might get some garbage out of it. If it's not your memory, you're gonna get a segfault out of it. So there's no bounds checking in arrays. They are kind of the wild, wild west, but they are fast, and they do allow for, aggregate storage of things. As we look at fixed size arrays, here's the sort of thing we're going to declare at compile time, I've got this int A1D, this one-dimensional array that's going to hold 9 values. If I'm going to put them in there, you can see they've got values 0, 1, 2, 3, 4, 5, 6, 7, and 8. Those are my 9 values. The indexes at this point match them up because I've filled this information in there. This doesn't show how I filled this array, but for the purposes of this demonstration, I've filled it with exactly what its index value is. So at index 0, the value 0. At index 2, the value 2. At index 6, the value 6, and so on. If I were to think of this 1D array as really a 3x3 array, I could do that. And what I would have to do is some additional math to think of this 9-item array as really 3 sets of 3. All I have to do is sort of divide that up by 3s, or take my division and remainder operator, that's the modulus operator, because remember, the modulus operator just performs division, but instead of returning the dividend, it returns the remainder. So I can use those 2 division operators to convert this 1D row of values into a 2D 3x3 thing, and I can just say take that index, mod by the number of columns to get the column. I can take that index, divide by the number of columns to get the row. And using integer division, this is going to give me something like 0, 1, or 2. On the far side, I've got a 3x3 declared, so that's int A2D. And there we've got 2 sets of square brackets to tell me how many rows I have and how many columns are in each row. So that's A2D square brackets 3 square brackets 3. And my memory looks the same in both of these instances, right? When I declare it this way, I've got 1 block of 9 values. And when I use this square brackets on there, the compiler does the math to figure out where to access data after my base address. That's all that's happening there. So as it's shown on the slide, there's this row of things here in my 1D and the square of things in my 2D. But in reality, they're all in memory, just one right after the other. So what we're seeing on the slide is sort of the logical version of these 2 arrays versus the physical version, which is identical for the both of them. In the far side, you see that that index for finding something in the 1D format would be taking the row times the number of columns plus what column we were trying to access, and that would give us the index there. So column and row here, index over there, interchangeable. They both can access these same things. So if you wanted to access a 5 on the far side, it would be giving you the same column and row here that you would find at the 5 in this index. Here's some use of it in C and C++. Well, it's really just a C version of this. So this is fixed size 2D arrays in C. It works in C++ as well, but this is C style code here. So we've got some constants here, rows and cols. I need those as constants so that I can use them in line 2 for this declaration where I've got this array that's made out of some number of rows and some number of cols. I can't do that in general in C++ or C with variables. There is a G++ extension that allows this to work with variables, but that's not fully portable code. So the goal here is to use code that can always be compiled and always can be run everywhere. So here we're going to use these consts so that we can declare that array of the right size. I got a size T for helping me cruise around there, my R and C, and then some value 0 that I'm going to use just to fill this. So all this piece of code here does from 1 to 10 is just fill that 3D array over there with the values as seen. It puts 0 and 0, 1 and 1, 2 and 2 in the first row, and then 3, 4, and 5 at 0, 1, and 2 in the second row, and then 6, 7, and 8 at 0, 1, and 2 in the third row. And those rows are, of course, 0 indexed, so the first row is index 0, the second row is index 1, and the third row is index 2. So this loop just goes through 2 nice little for loops there. Those of you who know how I feel about for loops really appreciate that these are beautiful looking for loops. This is what a for loop is for. This is for count controlled work. I know that it starts at 0. As long as I stay less than rows, I'll end up doing this rows times with a plus plus on there. So this is both linear, where I've got an R outer loop and a C inner loop. And oftentimes I'll see people say, well, this is n squared. This is not n squared. This is an R times C loop right here. This is the total work is, you know, if it's square, of course, in this case, because they're 3 and 3, this is n squared if we think of n that way, but this is not n. So I saw some students working with the back trace in project 1 and say, well, I'm really concerned about this n cubed loop here as I'm printing out these things at the end, but I say it's not n cubed. It's actually the colors times the number of rows times the number of columns. That's something that you can't get past. You can't do this without processing some aspect of that. So it's important to recognize that this is not two n's, right? This is rows and cols. So this is an RC. We've got these things here in my loops. I've got this plus C as my increment there. I saw the question there. I popped this one in there right now. But that pre-increment, what that does is it returns the value here, like the pre-increment, post-increment. It returns a separate value. And so after the post-increment or the pre-increment, the variable itself has the new value. But the pre-increment returns the value that we've already incremented it to, whereas the post-increment does the work, but still returns the value before the increment. So while C is a larger value, we're going to use the previous value when we post-increment. So the faster way to do this with these for loops is the pre-increment, because then we don't have to keep two copies. We don't have the current value plus the previous value, which is what happens when you use a post increment. It's a little subtle, but don't worry too much about it. Whereas in line 10, since we do want to assign the value 0 into one of our locations, we definitely post increment because I want to get that value 0 in there. If I had pre-incremented it, then instead of having 0, 1, 2, 3, 4, 5, 6, 7, 8, I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's what's going on there. On the far side over there, you see an alternate way to declare this array. Here I've got A square brackets 3 square brackets 3, and then we've done a static initialization where we've included the actual values in these curly braces with comma separators to make this look like exactly what we were trying to get. So a couple of different ways that I could fill that 3 by 3 thing exactly the way that I wanted to. This way with loops, that way with static initialization. It's important to note that these 2D arrays are set at compile time. The size of them are set at compile time. I can't change this stuff. This is why we love vectors. Vectors give me this dynamic work that makes things nice. This uses less memory than the pointer version. We haven't looked at the pointer version yet. In the pointer version, it looks the same in terms of square brackets, but instead of it being a pointer to one location, I've got pointers to pointers. And so when I dereference my outer level, I get a pointer to a row where things start. Let's see if I can make that a little bit clear here with this next slide. So here's what double pointers look like, and you can see a declaration here in line 4. It says int asterisk asterisk a. So that means that a is of type pointer to int. And then over in the diagram, we see A having this arrow pointing to a collection of pointers, the first pointer of which points to a bunch of integers. So there's the double dereference there. I've got a pointer to int. So in order for me to get a value, I have to dereference A 2 times. And the declaration there says I would like a new array of int pointers of length rows. That's what that very complex looking declaration in line 4 is. So in this case, you see that we've dropped the use of const. Here we've got some values, some variables, rows and cols in line 2 that we declare, and then in line 3 we use cin to read values into those. Now in line 4 I can do a variable length declaration, which is something that I can't do when I'm talking about doing it at runtime. If I don't know what rows is as a const on the previous slide, this isn't going to work. But this allows me to do this because I'm using new. New says at runtime, do a memory allocation, get me the things that I want. And in this case, this line 4 here declares that vertical array over there in the picture, the 0, 1, 2, that is just a collection of 3 pointers. Because rows is 3 in this case. We're imagining someone at this cin line has typed in 3 and 3. So with rows as 3, we get A as an array of size 3 of pointers to integer. So we've got things that can get us arrays, but I've got an array of them. So this is a 2D array with double pointers. I've got pointers for everything. Whereas the previous version, since I did it statically, or I did it at declaration time with fixed size, I didn't have to do pointers to pointers. So this is what it talks about when it says we save the memory overhead of double pointers, because now this same amount of data, these same 9 integers that I'm holding, has 4 pointers. I've got a pointer A to the array of pointers, and then I've got the other 3 pointers. So this has 4 pointers and 9 data values, where the previous slide had 1 pointer and 9 data values. So there's a little bit more memory overhead here. To go ahead and fill these things out, I need to make sure that I have arrays at the end of these pointers, which is what this loop in 7 and 8 does. 7 and 8 goes through each one of those pointers in A, 0, 1, and 2, and says, give me a new array of integers of size cols. So if someone puts in 3 cols, then each time I hit line 8, I get a new array of 3 integers. And I return that pointer and I assign it to a location inside of A. So now I can dereference A to get to an array and dereference that array to go over there and start finding those values. The loop here, as you see, is exactly like the previous pages, right? So in this case, we see how syntactic sugar is really working for us. Syntactic sugar here is doing something different. A square brackets R square brackets C is doing something different than A square brackets R square brackets C did on the previous page. The previous page was pure math. Just take that number of rows, multiply it by the first index, add the second index, and dereference there. Math, math, 1 dereference. This version of it, which looks exactly the same, says, well, first let's dereference at R and find where we're looking. That's going to give me a pointer to one of those arrays over there. Then I'm going to go to that array and dereference it at C. So there's 2 dereferences there. So this is a slower version of this. You can't get anything for free, right? I got this very flexible size now, but it's going to cost me 2 memory dereferences. Whereas when I didn't do the flexible size with the predefined size, I got 1 memory dereference. So it was faster, but I had to know ahead of time what it was. So what I've given up here is a little bit of speed, but what I've gained is the flexibility of not needing to know at compile time what I need. So you can't always get away with everything. So here we've got a trade-off that this isn't something you fight. When you have to do it, you have to do it. You don't get mad about it. If you say, well, if I don't know the size ahead of time, then I have to pay the price of flexibility. And you do it. And this is how you pay that price. We've got a 2D array here, and we can fill it with the exact same code, but fundamentally it's working a little bit differently, which is pretty strange. Thank you, compiler, for making syntactic sugar possible. On the far side, lines 17 through 20, this is how we undo all of the doing that we've done. So we started out here with a declaration of our outer array. Then inside this loop, we declared our 3 inner arrays. On the far side, we delete our inner arrays in a loop, and then we delete the outer array on the outside. So we've used new with square brackets in line 4. We've used new with square brackets in line 8. New int square brackets calls. So this is a new square brackets, we call it. And the way that I have to undo new square brackets is with delete square brackets. So these 2 calls in 18 and 20 are delete square brackets that undo what has happened in 4 and 8. That delete square brackets is important because the compiler needs to know that at that location we need to delete more than just 1 integer or more than just 1 pointer. The compiler handles this all for you. Actually in memory right before the first pointer, it sticks that size so that subsequent calls to delete square brackets actually delete the right amount of information. So that gets kind of deep into the way that the mechanics of compilers and stuff like that works. So don't worry too much about it. It's important to note, though, that delete square brackets matches up perfectly with new square brackets, and they have to be used hand in hand. If you use new, you use delete. If you use new square brackets, you use delete square brackets. So the pros and cons here of fixed versus pointer-based arrays. I know that these fixed ones are allocated on the stack. They're right where I declare them. They're in that stack frame. So the great news about that is as soon as it goes out of scope, it's gone. I don't even have to delete it. The memory for all of that was declared and held in the stack frame. It gets freed up when that stack frame goes away. We saw that I talked about A square brackets, I square brackets, J uses only 1 memory operation, not 2, 1 dereference, even though it does a little bit more math, right? right? 1 dereference, not even more math. We're gonna have to do the same amount of math when we do 2 dereferences. It just does the 2 mathematic operations and then the 1 dereference. The cons are it doesn't work for large N because this stuff is stored on the stack. So if I've got too large of a 2D, 3D, ND array, all of that memory has to go on my stack frame. If it gets too big, I can cause a crash there. I've got more space in the heap. If I need to have enough size, I need to make sure that gets put in the heap, even if I know sizes ahead of time. So it is fixed at compile time. It's difficult to pass as an argument to a function because we need to know what that size is. We have to pass in the pointer, which is the base address of this 2D array. And then we also have to pass in a row width. So how many items are in each row so that the memory in the called function can be accessed properly. One thing we also want to do here is when we're doing this fixed size at compile time, it leads us to a situation where if we say, well, I don't exactly know how much I want, maybe I'll just do a little bit more and I'll definitely have enough space there, right? So what that does is says, well, since I have to do this as fixed length, even though I've got variable length data, I'm going to overshoot there, which can lead to some really serious problems. Security breaches find ways into looking at extra declared memory. So we would like to avoid a fixed length buffer for variable length input. So if you know how long your input is, then you want to get a buffer that's that size. What by buffer, I mean any memory allocation. So if I know I've got 15 ints, I would love to have 15 ints worth of space before I start reading them in there. So one thing that you don't want to do is say, well, I think I've got some string coming in. I'll just declare myself a K. Give me 1,000 bytes, and then I'll read whatever the user gets in there. I mean, no one would ever put more than 1,000 bytes in there, so I'll be fine. So there's 2 things that could go wrong there. A, someone could put more than 1,000 in there, and then you write off your memory segment, and you've got some error. But B, when you allocate 1,000 bytes, the compiler just finds them and gives them to you. It doesn't find them and clean them out. It doesn't do spring cleaning. It doesn't paint the walls before you move in. It just gives you that memory. So whatever was in that memory is still there. If someone had their password file loaded into those bytes and then passed that 1K off to your program, you could just cruise through the memory and see what text you could find in there. So this is why we say avoid a fixed length buffer for variable length input.
Missing all the keys.
Oh man, we got a key situation here. Stand by.
Sorry, I can't find either key nor the.
Sorry. All right. Life inside, making this happen. All right, we're talking about dynamic allocation here. Now we talk about that double pointer things. We got double pointers. These are arrays allocated on the heap. Now, the pro is, of course, the memory's on the heap. So I can make this live outside of one particular function call. So if I want to have this persist past one function or have this memory pass from one function to another that might not have to be in the same call stack chain, I want to do this later, I have to do this dynamically. So the pros are I can support triangular arrays, which is something you can do to save memory when you've got, say you've got a 100,000 by 100,000 matrix that's got some diagonal symmetry. You don't have to have all of those elements in there if I only need half of those elements, because I can have a sort of triangular array or even sort of ragged edge array. So I might have 50 rows, but each row might be of variable length, which I can't do that with a static declaration. But with a dynamic declaration, I can say, well, row 50 needs to have 10 items, row 30 only needed 12 items, and row 27 needs 100 items. You can do that with dynamic declarations. This allows copying, swapping rows pretty easily. If I want to move an entire row in my static declaration, I have to make some space, copy all of the things out of it, then copy the things into where they used to be, and then take the stuff out of temp just as a normal 3-item swap. Whereas if I've got these dynamic pointers, I can swap rows really simply just by swapping pointers. Now, I still have to do a 3-item swap, but instead of my 3-item swap being all of the data in the row, it's just the 2 pointers that are at the head of the row. So I can get that done in a constant amount of time as opposed to a linear amount of time. Size can be changed at runtime, which is good. That's what dynamic is all about. The cons are, of course, you have to memory manage. So you have to do the news, you have to do the deletes, and you have to do that well. If you do it poorly, you can crash, you can leak memory, jump off the end of things. bad stuff. And we also talked about A square brackets, I square brackets, J being a little bit slower than with the built-ins because we do have 2 memory dereferences. So it's a little bit slower, but we've got pros and cons on both of these things. C++, of course, STL gives us a cleaner solution, which is the vector. To be sure, the vector is doing all of this dynamic stuff. It's just doing it for you in a way that's been debugged by numerous people and happens in a very safe way, right? So that's why we appreciate the vector. But if you want to think about, well, is the vector going to be faster for me than doing it myself? It's not. It's not going to be faster, right? It's going to be as fast as possible. You could write it probably equivalently as fast if you were very careful, but it's not guaranteed to be faster. It's just guaranteed to be nice. It's syntactic, vectors are syntactic sugar on dynamic arrays. That's what it is. It works very well. It's debugged. It's got some member functions. It does these things really nicely. So that's why we like to use it. It makes code easier, faster to write, faster to debug, easier to understand when you're reading someone else's code. And, you know, that's kind of the way that we're working here. In the ancient days, when every bit of speed counted, we were really concerned about doing things manually and using our own pointers and writing our inner loops as fast as possible. Now we've got just an abundance of computing power, abundance of computing storage. And so a lot of times, good enough is good enough. And vectors are really good. They're definitely good enough. How about some off by 1 errors? These are things that bear repeating, so just make sure that you understand what's going on here. I've got a const size that's declared with size 5, and I've got an array of integers of size 5 named x declared, and then I've got this size t that I'm going to use to slip through it called I. I've got some for loops here, and you know me and for loops. I really like a nice for loop. Line 6, that is not a nice for loop. I've got I equal to 0, I less than or equal to size. That shouldn't be there unless I really want to. And this is a great place to have a comment. If you're ever going to do something where it's like I less than or equal to size, you better put a comment in there as to why you're doing something abnormal. Someone's going to look at that for loop and just start scratching their head. Why are they doing 6 of them when I only have 5 of them? So that's an off by 1 because this is going to attempt to do 6 things. And if I'm doing it with X, I'm square bracketing 6 things in there. There's no way that's going to work. So this is going to be something that should be less than size. How about this next one? So here we can see that we're trying to do something in line 11 where x at I is equal to x at I plus 1. So someone's trying to do a shift thing. So it makes a little sense here where you might have an off by 1 here where I see a size minus 1 in the comparison. I is less than or equal to size minus 1. Well, that gives me the right number of them, right? Because when I say I is less than or equal to size, now that gives me 1 too many. If I say I is less than or equal to size minus 1, that gives me the right number of them. But it ends up still letting me hit on to 4 as my index of I. And down in line 11, I see I'm putting something at I plus 1, so I can get to 4. If I say I plus 1, that gives me x at 5, which is not my memory. So that's an off by 1 error as well. The last one here, somebody tried to do something differently where it's a minus 1 on the indexing. So we start out as I equal to 1, I less than size. So now we know that if we're thinking about this, which we shouldn't have to do when we look at for loops, we shouldn't have to think about them. We should just know what they're doing. I should know that this count control loop is going through all of the things. Unless there's a comment to tell me specifically why I am skipping a thing or why I am offsetting things, right? So here we're trying to go from 1 to instead of sort of putting the values in there as 0 index, 0, 1, 2, 3, 4, we would maybe be trying to put them in there as 1, 2, 3, 4, 5, sort of like human counting style. But since we started at 1 and still went to less than size, we don't have enough of them. So we're still not setting them all, right? 1 up to less than size is now 1 less than the total number of items that I need, so I don't get enough. So this doesn't fill all of the values, and you should be using I less than or equal to size here. So 3 perfectly good examples as to why you don't futz with for loops. Write them from 0 up to less than the thing. That's how you get there. If you have to do a reverse for loop, be very careful about that. Make sure that you're not using size t's and subtracting 1 and hoping that you'll get below 0. The size t's never go negative. Even when you subtract 1 from 0, you don't get a negative number. It's an unsigned data type that then loops around to 18 quintillion, and you never have a value less than 0. Your compiler will catch this, but if you're not thinking, you can end up in a poor way there. And if you start trying to manage that by being greater than or equal to 0, things get pretty hairy though. So be very careful. Oftentimes it's easier to just make that for loop just count controlled from 0 up to less than size, and then whenever you use it, subtract from size and use that to do your reversal. That makes the code really easy to read. You don't have to worry that much about what's going on in the math there. So be careful with your off by 1. How about range-based for loops? Those are nice. Those are new from C++ 11 and beyond. So it allows me to do things like, instead of having to write this is a nice for loop. I like this nice 0-based for loop. This one is great. That's classic and stylish. 2 thumbs up, right? But this second version here in 9, that's a ranged based for loop. So now I can say for item in container or for item in array. And we see that we've got for loop, and then inside the parentheses there's int, which is declaring a variable for me, and a colon, and the container that I'm looking at, which in this case is my C-style array. So what it does here is it goes through and assigns a value to item for every one of those values in my array. Sorry, there's just bad internet going on across the world here. I don't know what's going on. Maybe it's just my room. Maybe it's my house. My house is empty. I'm solo on the network here. But before I got on, my daughter was having problems with the internet, and we reset all the hardware, and I don't know, the school is reporting internet problems. I don't know where all the problems are. I apologize. I use my magic wand and improve the internet. Maybe we need some infrastructure. But it's important to note here in line 9 that item has an ampersand in front of it. This means that we're declaring item as a reference variable. So item is not an int, it's a reference to an int. So the integers that are inside of my array can be changed. Here in line 10, when I say item times equals 2, since item is a reference, I'm making changes inside my array. If I don't include that ampersand, then item gets the values from my array by value. So that means it gets its own copy from my array. And then this math here on item has no bearing on what's going on in my array. So it's important that if you want to change what's going on in my array, or if what's in my array is an object and you don't want to make a copy of it just because you need to reference something, you need to use that reference declaration in there. So the reference declaration is optional. You need to know when to use it and when to leave it alone. Here, this range-based for loop works on a C-style array. It also works on C++ style vectors. Anything that we know the size of, we can for loop over a deck here if we'd like to. We can for loop over a linked list with this range-based work here. So be aware of that. This is how this works. Range-based for loops can either be done by value or by reference. Here's my strings as an arrays example, because strings are just arrays of characters. So in line 2, we've got this declaration of name with 20 square brackets in there. So this gives me 20 characters, which I can treat as a string as long as I make sure the last one is a null terminator. So if I was to use this, then the longest name that I could actually represent in there would be 19 characters long. Then I stick in the null terminator, I'm good. If I want a 4-character name, I got 4 characters and a null terminator, it works just fine. Stir copy is going to go and copy into name from argv. Argv square brackets 1. So we go to that pointer and dereference things there. And the stir copy function is a string-based function. It takes 2 strings, C-style strings. And so a C-style string is really just a character pointer. And since we declared name as an array of characters, name is then still a character pointer. An array of characters, that variable is still a pointer to character. So I've got a pointer to character, and then of course the declaration from line 1 shows us that argv square brackets, that's an array of character pointers. So if I dereference that argv at 1, that's going to give me a character pointer. I'm passing 2 character pointers to stir copy, and that function is a string function, just says, okay, I'm going to start at argv1 and just keep moving those things one at a time into the name. And I'm going to stop when I see a null terminator at argv1. And just because stir copy loves you so much, it's going to slap a null terminator at the end of name. That's how it does things. So what could happen here? We see we've got a nice little bug over there, just trying to make life difficult for us. What are the errors that could occur here? Hopefully you've seen them both already. I already talked about the problems with fixed length buffers. That's declaring something of size 20. So that's fixed length is 20 no matter what. There's a fixed length buffer. So if my name is longer than 20, I've got real problems. If my name is shorter than 20, I may be giving away some data that I think is important. So I want to be careful there. So that's one possible error. And hopefully you were defensive enough to understand that argc is there for a reason. Argc will tell me if I can even look in argv at 1. I might not be able to do that. If argc says you don't have 2 things, argc says the value is 1. All you have is the command. You don't have any arguments. Then argv of 1 is that's not out of bounds. That's something that's jumping into somebody else's pointer. So those are my errors. I can make this safer with some nice C++ stuff here, right? There's the first test, line 8. If argc is greater than 1, I can even access argv at 1. Then what I'm going to do is take this C-style string, which I've C++ string, sorry, STL string name, and then I can assign this C pointer to it. And that's an overloaded a conversion assignment. Conversion assignment. So I can assign a C-style pointer to a C++ string, and the C++ string says, oh, I know how to do that. I'm going to go check the string length, make sure I've got that much memory, and then copy all of those values to wherever I think that memory is, null terminate it, update my size, and move on. So this one will make sure that I've got enough memory to hold what I need, don't need to have more. Then when I come out of this, I've got this thing that's going to go away. When I exit main, the destructor is going to run on my string, and then things will go away. Looking good and bug-free. Here's a quick set of job interview questions that can take some thinking. These are some good ones to think about. Hopefully, do something this when you're relaxing. I'm hoping that you do some algorithms while you're relaxing. Oh, come on, prof. All right, assume that a given array has a majority element, meaning some element is in there more than 50% of the time. Find it. Find out what that element is. So this listing 11, 13, 99, 12, 99, 10, 99, 99, 99. That's got 9 values in it, and it's got 5 99s. So that fits the bill there. I've got some element that exists more than 50% of the time. So the question is, can you find out what that element is in linear time with only a constant amount of memory? That's what's there. So that's one really difficult challenge. The next one is even more difficult. Do the same thing for an array that has some element that repeats more than a third of the time. So if it's more than a third of the time, how do I find that one? So here I've got 11, 11, 99, 10, 99, 10, 12, 19, 99. So I've got 3 99s in this collection of size 8. I should be able to find that. You can start by looking up the Misra-Gries algorithm. That's spelled MISRAGRIES. You do something like that after you've done plenty of good hard thinking. These are what job interview questions are all about. Spark that thought. So if you can't get to the answer, go check out Misra-Gries, and you can then start to understand what's going on there. That's our coverage of arrays in C and C++. We see how we've got these pointers, we've got square brackets notation, we've got dynamic or static declaration, we've got some syntactic sugar in there, we've got pointers of dereference and all kind of good things. So figure out how arrays work, because it's fundamental to the way that the memory model works as we start doing things. Up next, we're going to talk some more about containers. We've already talked about a few containers: stacks, decks, queues, priority queues. We're going to talk more about containers. These container classes are objects, of course, that contain multiple data items. We can put some built-in types in there, like ints, doubles, bools, characters, and whatnot. We can also put objects in some of these containers. They allow us to control the data, or sometimes it can keep protection. So that in the case of, for instance, like a queue, you can't access the thing in the middle of the queue. So containers can do that work for us. It allows us to do aggregate operations as well, like copy all of these things or do a sort on these things or something like that. We can combine containers to make more complex data structures, containers that hold containers. This is really what a database is. A database is a collection of tables. A table is a collection of rows. A row is a collection of fields. And a larger database has multiple databases in it. So this is a container of container of container of container of container of container of containers. So we do put them together quite a bit. So the examples that we'll be looking at throughout the semester, of course: vector, list, stack, queue, deck, map, unordered map. I said list in this list, but we'll be looking at it. We won't be looking at list in 281. We're not going to do a whole lot of work with list. That's the linked list, and we're going to be working with just about everything else but the linked list here. So one thing I like to say is, if you're in 281 and you think you've come up with a great reason to use a linked list, it's time to go back to the drawing board. Try to think some more. So you can use them later in life, you just won't be using them too much in 281. By too much, I mean zero. Of course, then there's the STL that has those things with us. Most of our data structures in 281 are going to be containers. We'll be looking at things that do ordered and sorted ranges. We'll be looking at heaps, hash tables, trees, and graphs. We're going to do this example today, which is how do I make an array-based container that has bounds checking on it. So I'm going to use this for my illustration purposes. We'll be looking at some code and sort of talking through it. When I look at a container class, I'm going to look at some fundamental things that I'm going to need all the time. How do I make them? How do I break them? Or how do I get rid of them? I need a constructor and destructor. Most containers aren't worth anything until you put something in them, so I do need to add elements on a regular basis. Some containers you also need to remove elements from. Not all of them, but some of them you do. So add and remove element is also a pretty common thing to do with containers. How do I retrieve an element? That doesn't mean remove it. So how do I get it while it stays in the container? Can I check the size? Can I make a copy? Can I assign something? Blah, blah, blah. So there's a lot of container class operations that we have, and almost every container has a really large subset of these 8. However, there may be some other operations that you can think of that might be useful. So this is just a thought exercise as well. How do we access items in containers? I can do this in 2 ways. Some containers allow sequential access, which means I've got a way to get to the beginning, and then if I want to get to anything else, I have to start moving in through there one at a time, sort of like moving through a linked list with next. So that has sequential access. The only way to get to the 5th item in a sequential access situation, next until you get there, right? So that's what hard disks in computers use. At least our old hard disks, our spinning hard disks, used sequential access. Random access, of course, is what we're used to in arrays and vectors of stuff. So I can say I want to find the nth item. I can just start at the beginning and jump to that nth location in a constant amount of time. This is how arrays access data. This is what main memory of the computer does. So it's much faster than having to spin up a disk and look through things. Arrays can still be, of course, processed sequentially. You can always start at the beginning of an array and then just move your index over by 1. But I don't have to only travel sequentially. Let's look at copying an array. How do we copy from some sourced array to some destination array? So that's my convention there, my naming convention. In line 2, I've got a declaration of source array that has 3, 5, 6, and 1 in this collection of doubles. In line 3, I've got a destination array that has just enough room to hold all of those doubles. And we can see that we did an implicit size declaration in line 2. We did source away square brackets closed so that it's empty. And then we did in an explicit initialization. So that made source array have size 4. We couldn't do that for the destination array without putting something in there. So in this case, we used a constant there, size, which has a value 4 in it, so that I can declare destination array to hold 4 things, enough to hold what's in source array. This is a nice for loop way to do things. We know ahead of time how many there are. There's size of them. I can use this really nicely written for loop, 0, I is equal to 0, I less than size, plus plus I. That's great. No pointers involved. I just say what's in destination array at I should be equal to what's in source array at I. This is a straight up for loop array copy. This next version, however, uses pointers to get around there. So now I've got 2 pointers, a double pointer, which I call S pointer, which is going to point into my source array, and a double pointer, which I call D pointer, which is pointing into my destination array, and set both of those things equal to the beginning of those 2 arrays. So double pointer S pointer equals source array, double pointer D pointer equals dest array. Now my while loop here now is a while loop now. It's not count controlled. This is a while loop. We're going to keep going as long as my source pointer hasn't gone too far. And too far is the source array plus the size. So source array, of course, is a pointer. So if I take source array plus size, source array plus 4, that's another pointer. So when S pointer hits that pointer location, 4 locations after the beginning of source array, then that's where I need to stop. And that's going to be working on that 0-based indexing. So at source array is good, source array plus 1 is good, source array plus 2 is good, source array plus 3 is also good. Those are the 4 things in there. But source array plus 4, that's not good. You don't want to dereference there. So that's why the while loop says, whenever my source pointer gets here, stop reading. Stop reading at source array plus 4, because that's too many. Other than that, I just dereference destination pointer to write and assign it to dereferencing source pointer to read. When I get done at the end of that line, I've got 2 post increments that are going to move both of those pointers forward. So this is how my while loop behaves. As long as my source pointer hasn't reached the end, do this writing, and then the writing gets followed by a post increment and source pointer moves. That allows us to proceed until the while loop condition fails, and then we stop copying. So this, in line 11 and 12, does exactly what a line 5 and 6 does. And of course, you must be thinking, why would I bother? Why would I use pointers when that code without pointers, you said don't use pointers? Why do that when it looks so much nicer here with a nice for loop instead of this while loop and all these pointers and plus plus increments and comparison and the size and all kind of badness? I'm looking at, there we go, speed it up. So why do that without them when I could do it the other way? Well, one thing is we'll be looking at later is generic programming. And this generic programming says, if I've got anything that I can use like I've used these pointers, I can compare 2 pointers, which I did in 11. I can increment the pointers, which I did in line 12. I can dereference the pointers for read and write, which I did in line 12. If I've got anything that behaves like that, this loop can be used to copy it. What else behaves like a pointer? Well, it turns out that iterators behave like pointers. Iterators can be compared. Iterators can be dereferenced for read or write, if you got the right kind. And iterators can also be incremented. That's what iterators do. So with this type of copy here in lines 11 and 12, if I've got 2 iterators, even if they're iterators into different types containers, and have an iterator to a vector or an iterator to a deck, it's going to work. All right, what do we store in containers? What type of data? Do we put stuff in there by value? Do we put stuff in there as pointers? Do we put stuff in there by reference? So we'll look at those, whether we do them, and then we also look at how do we get something out of a container, but not remove. How do I look at something, I should say, in a container? So when I get it from a container, I'm going to leave it in there, but what do I pull out? Do I look at that as a value? Do I look at that as a pointer or a const pointer? Do I look at that as a reference or a const reference? So I know it's a little murky about what the distinction between a pointer and a reference is. You can think of references really as safer pointers. So if I were to stick things in there by value, then the data is owned by the container itself. If I were to put things in there by a pointer, so the container has pointers to things, whoever has control of that pointer can say, well, that pointer is no longer valid. I'm going to delete that pointer. And then your container is left there holding the bag, holding a pointer that's dangling off into infinity. So we don't have control over data ownership when we put stuff in there by pointer. We do have control of the data ownership by the container when we put it in there by value. The drawbacks, of course, is when you put a large object in there, we've got to copy those objects. We make copies of them, stick them in a container, maybe destroy the local copy. This is usually how we do things. So we usually put things in containers by value. We try to put them in there by pointer. It's very unsafe, because I mentioned before, it moved, and that's not good. So if I've got a vector holding things, and I say, well, I'm going to give you a pointer to something in my vector. Sounds great at the time. Then somebody adds something to the vector decides, we don't have enough space here. Let's move all of these things somewhere else. Now that pointer that I passed off to one of my items is no longer valid. So it's very, very dangerous if you start putting pointers in containers. You have to make sure you don't lose sight of where those pointers actually are, because the container doesn't have control. When I'm putting references in a container, that's pretty difficult. You can't put a reference in there. References have to be initialized. You can't say, well, I've got a vector of array references, or I've got a vector of references to integer. I'm going to run through this loop and say, you've got a reference to that integer. You have to initialize references when you declare them. You can't assign to one later. So it's impractical. You almost can't even get that done. When we get things out of a container, though, we've got the ability to bring it out by value, which is fine if you just want to pull something out and use it. Use it locally. You don't worry about making changes to it, right? So if the value says, I'm bringing that value out, it can be costly because I am making copies. If I got large objects, you want to be careful about that. If you've got an array of integers and you just want to pull things out by value, that's fine. You just make a copy of those integers and you use it for the copy for what it's worth, and you move on. Sorry about data. I don't know. We'll have to do something else. Maybe I'll try something else tomorrow and relocate. Pointers, pointers, same sort of thing. If I give you a pointer to what's in this container, if I decide later as a container I need to move, and I've given someone else a pointer and said, well, here's the value that you need, but I need to move, there's no way to tell that other container or that other variable, that other program, oh, by the way, we packed up and moved on. We're not here anymore. Don't come calling. So it's pretty unsafe in the same way that putting things in there by pointer is unsafe. We do often return things by reference, and that's good. We can use reference, or we can also use a const ref. In a const ref, we can say, here's a reference to this value. You can look at it, but you can't touch. The thing about references, though, it keeps us, like pointers do, it keeps us from having to make copies. So usually it's a good choice when we have our containers. We'd like to get them to return references to values inside them. This gets into the touching on memory ownership. Here we've got two pointers, array A and B. We know that arrays are really just pointers. So if I've got two pointers pointing to the same memory, and I've got this collection of these 5 colored dots, A is pointing to it, B is pointing to it, I can look at A square brackets 2, and it's going to be the same thing as B square brackets 2. When I modify A square brackets 3, it's the same as modifying B square brackets 3. So sometimes you want to do this, but it's a very rare occurrence. So you don't generally get into something like this, because then you have to be very careful about how you delete this. If I get done with this, I said, oh, I'm all wrapped up, so I'm just going to delete A. A deallocates that memory, and then some other part of the program says, hey, B, what's that square brackets 3 again? B doesn't have access to that memory anymore. B still thinks it does. It's still pointing there. It still takes its base address, offsets, and dereferences from there, but that can cause garbage. It's just grabbing something that some other program has used. It can also cause memory segment faults, because if you don't own that memory and you start dereferencing it, you can get a pretty serious smackdown from the runtime that says, you can't handle this. So this is a problem, so we have to be careful about memory ownership, make sure that our objects handle that properly. The memory ownership issues we have as we look at copy constructing an assignment. One way to do a copy construction assignment is to note that duplicate objects get created. When I do an assignment, I say object A is equal to object B. If I don't add any of my own copy constructor or operator equals. It just does a member by member assignment. So, I've got a value int, I've got a value double, and then I've got a pointer to a bunch of characters. When I make a copy of that, the new one gets a copy of the int, it gets a copy of the double, and it gets a copy of the pointer, which leads us to that A-B situation we saw on the previous slide, because if I just give some other object a copy of my pointer, it doesn't have its own copy of the data, then I've got that situation where when I delete one of these objects, it's going to delete the other object's data because it doesn't have unique data. So we have to be careful with that. And make sure that when we have something that's using dynamic memory, if we're writing our own object, we have to make sure that our copy constructor or operator equals goes back and allocates and makes what we call a deep copy. So if I've got a pointer to some memory and then values in it, and you want to make a copy of me, I have to tell you how to get your own pointer to your own memory with the same values in it, and that's a deep copy. One way to do this is to make sure that every object is owned by a single container. We like that. Another way to do this is to say, I'm not going to use any ownership. I'm just going to keep track of who references things. So imagine that slide previously where A and B are pointing to the same memory. So in a system like Java, which uses garbage collecting, it says, okay, I've got 2 pointers to this location. So when object A gets destroyed, now I've only got 1 pointer to this. I've only got 1 item that's referencing this. So it keeps track of these reference counts or ref counts. So when the ref count goes to 0, nobody deletes the memory because nobody's in charge of deleting memory. Nobody owns memory. But later on, the garbage collector just kind of from time to time rolls by and looks at these things that have already been allocated. It says, wait, there's no references here. That means no one can reach this memory. I'm going to just clean it up now because it's gone. Well, here's a block of memory someone allocated at one time, and I can still see that there's 3 pointers in there, so I'm going to leave that. 3 objects still think this is good data. When one object goes out of scope, it doesn't destroy anything. It just says, I'm done. I'm no longer referring to that memory. Now there's only 2 of them referring. And the garbage collector says, oh, there's still 2 refs. I'm going to leave it alone. When it gets down to 1 ref, I'm still leaving it alone because someone is counting on that memory. But when that last object goes out of scope, gets destroyed, whatever, and it cuts that reference count down to 0, then the garbage collector comes in and sweeps things up. So that's the way that smart pointers work. We don't do that in 281. We want you to make sure that you can handle memory yourself, make sure that you can declare and allocate and deallocate and do all the things that you need to do in a very good way before we start getting some help from things like smart pointers. So it's important to recognize with pointers that some object could be owned by another container. Right? Containers may not allow access to objects inside. This is for privacy. It's also good for safety. And this is going to help us sort of prevent the deletion of the same chunk of memory twice, because when an object owns the memory and it doesn't allow you to delete from it, then we have a smaller chance of having a double delete error. The destructor does have to delete those things though, so you have to be sure that anything that's got pointers, that has memory, that has stuff allocated, we've got some way to get it cleaned up. Here's our defensive programming tip here. Instead of just calling delete on a pointer, set that pointer to null pointer after you get done with it. What this does is it makes sure that anything that accesses that pointer instantly fails. This is good because sometimes if we delete a pointer and then we can continue to read from it, sometimes what was there is still there. And so it looks like our program really is buggy, because the true definition of a bug is something that sometimes behaves one way and without code can still behave another way. That's really what a bug is. Everything else that we talk about most of the time debugging is just an error. You did something wrong. So a real bug can be found when you delete something and then you access what's at that pointer, because for a while it's exactly what was there before you deleted, but after some memory movement there can be different information in there, and so later on when you access it, it doesn't work. So when you delete a pointer and you set it equal to null pointer, the next time you try to access it, it instantly crashes, which is good. We want things to crash that are illegal. We fix them so that we don't do the illegal thing, but we don't want something illegal to work sometimes and fail other times. It makes it really hard to figure out what's going wrong. It's also important to note that if I try a delete on a null pointer, I don't get an error. in the old days, we used to set null equal to 0 and just set a pointer equal to 0, which did the same thing. It allowed us to fail right away when we tried to dereference here. But if you tried to delete a 0 pointer, you're going to crash. Whereas if you try to delete a null pointer, it says, oh, you're trying to delete some memory that's already gone. It's okay. We're going to move on. Okay? So setting that thing to null pointer is a nice defensive safety thing. Helps prevent bugs. Helps prevent memory leaks as well. Why do we care about memory leaks? Well, when our program gets done, all of the memory that it used should be freed up. The operating system is going to do this most of the time for you, right? The OS will deallocate the memory that's in there. However, if you're running along and you're continually losing memory, so you sort of allocate something and then you sort of set the pointer equal to something else without deleting it, that memory is still reserved for your program. And no other program can use that. Your own program can't use that memory anymore. And if your program does this often enough, then you can end up using all of memory even though no one has access to any of it. This causes the crashes that later give us many problems. This is what was happening quite regularly in old Windows. Windows 3.1 and previous, those things were really, really leaky. They'd lose stuff, and if you were working sort of like an office job, you would have to reboot your machine 2-3 times a day just because it would slow down and slow down and slow down reallocation. It would have to look harder and harder to find a block large enough to get what you wanted, and then when you leaked it, you left it already reserved and unusable, you would have smaller and smaller places that you had to look for memory, and so your machine would slow down. Eventually they would lock up, and so that was why many reboots would happen. One way that you could get around this is, of course, to use Valgrind. You should always use Valgrind. Unless you're certain that things are working great, make sure you use Valgrind on a regular basis. It's just, it's something you need to do periodically throughout the development cycle to make sure you haven't done anything wrong. It's kind of a real headache to get the whole thing done and say, okay, I'm done. Let's try Valgrind in this thing. No, then when you got a problem, it's really difficult. So pop over to Kane once a day or once every other day, upload your code, run it, Valgrind it, make it work. All right, that's my talk on containers. I've got a few more minutes here. We're going to get into this bounds checking array. This bounds checking array is an array that's going to allow checking of bounds, meaning when I try to go square brackets, if I square brackets outside of the array, it's going to tell me, hey, that's a problem, instead of just seg faulting. That's what the goal is. So to do this, I'm going to need some dynamic memory. So this is just a little review on dynamic memory. When I call new, it uses the default constructor to create an object. When I call new square brackets, it gives me a collection of objects, but calls the default constructor on each one of them. We don't have to call constructors, of course, when we're talking about basic types, ints, doubles, floats, bools, and things like that. But objects that have constructors get default constructor calls. So you can't make them custom, say, well, I would like a new array of these things, and I want the first one to be initialized with 1, the second one to be initialized with 2, third one to be initialized with 3, so on. You can't do that. You just get the default constructor. Delete, of course, invokes a destructor. So if I've got an object, it's going to destruct it when I call delete on it. It'll tell that thing, I'm calling your destructor. I don't need to destruct built-in types. I don't need to destruct ints or doubles and that, so those don't get called. But delete square brackets, much like new square brackets, does things in an array fashion. So new square brackets called a bunch of default constructors. Delete square brackets calls a bunch of destructors, one for every object in there. So you always use delete with new. You knew it, then you delete it. You always use delete square brackets with new square brackets. You new square brackets them, you delete square brackets them. So here is my header, my H part of my class. So I've got some things that I would like to declare and then define outside of the class. Other things I may define inside the class. Here, so I've got class array, and you see that it's got 2 private members, a size t that tells me how many things are in there, we'll call that length, and a double pointer, which is where my data is, which I'll initialize to null pointer. I've got what's called static initialization going on in lines 2 and 3. I set length equal to 0, I set data equal to null pointer. So when I make a new one of these things, by default they already start out with 0 and null pointer. I don't need to make a constructor to do this. So this is a great way to make sure that everything in your class /struct gets initialized. You can use static initialization everywhere that you can do things statically. Now, if I need to do something dynamic, I obviously can't do a dynamic initialization here. So this handles all of my values, and it's a wonderful, wonderful way to program to make sure that everything in your object when you create it is initialized. Here I've got two members. I know that they're both initialized before I start. I've got a constructor declared here in line 6, array. That's my array. That's a function that's named the same as my class and has no return type. That's a constructor. And this one is a custom constructor because it takes a value. It takes a size t as a length. And then I've got an initialization list that follows that. So it's array size t len. Then I've got the colon that begins the initialization list. And there I can initialize one or more of my member variables. And I have to make sure that I initialize them in the order that they were declared. So I can't, in this initialization list in 6, I can't initialize data before length. I have to initialize length before data because length was declared in line 2 and data was declared in line 3. If I want to do them in a different order in the initialization list, then I have to declare them in a different order before that. You can see my destructor here is going to do a delete square brackets at data, which is fine if I just create one with nothing in it and then turn around and delete one. Remember that deleting from a null pointer is not a problem. So delete square brackets at data, if it was still a null pointer, still no problem. And then I do this defensive thing and set data equal to null pointer when I get done. So that's my destructor. It takes care of things. If I wanted to be extra pedantic, I might set the length equal to 0 on destruction, but since this object is going away, there's no real need to do that. I've got this size function, which is just like you measure the size of a vector. You say how many items are there, and this is pretty simple. It just returns the length member. And we see that that size function is declared as const, which means when I call size, there's no way to change this instance, which is good. I'm only measuring it. I don't want to make any changes. So calling size is a const function, and it just returns the size t by value, which is great. We don't need to do referencing there. It's not an object. It's a built-in type. We can just return that by value. So that's what 13 does, return that size by value. Now we're going to have to look at this constructor. You see that in the initialization list, line 6, we set length equal to the passed in len, and then we can also set data equal to a new double square brackets of length items. So that's going to give me a pointer, sets data equal to a pointer. So if I call this constructor with some length greater than 0, it's going to give me some array of doubles. Question here is, should I use a class or struct? Turns out that at compile time, they are a 100% equivalent. Not larger, not faster, not slower, not smaller, nothing. Class and struct are identical. At compile time, what's in the public section versus what's in the private section is the only distinction in class and struct. Without a message, everything in a class is private. Without a message, everything in a struct is public. Here I've got this label that says everything after here in line 5 is public. So I've taken a class and everything before that public is private, and then after the public, everything is public. So if I wanted to do this exact same array with a struct, I could do that by putting a private before my member variable declarations and then putting a public for my public functions, and it would work exactly the same way. So normally I like to do really simple things that are just data, like say I've got some color row col thing. There's not a whole lot of work that does. I kind of pass it around as a way to aggregate data. For me, I put those in structs because they're not going to be doing their own work. Here we've got this array class that's going to be growing later or allowing access. This is going to be doing some work, so I would put this in a class that tells anyone else reading the code that this is not only a collection of data, but it's also a collection of functions that work on those data. So that's what's important about the distinction between class or struct. Here's my copy constructor. I see that it's a copy constructor because it's a function named array that is the same as my object, and it's also got a const array reference passed in. That is what the copy constructor function template looks like. Not function template. Function declaration looks like, right? So I'm declaring this, and I'm passing in some array reference A, some const reference A. So I can't change anything in A, but I can make this, the object that's being constructed, I can make things change inside there. So I'm going to do this with my initialization list. I set length equal to A's length, and I set data equal to enough memory to hold all of the data in length, but I can't update that in my initialization list. So that's when I get into the body with this for loop in lines 4 and 5. I run through the things that are in A's data and copy them over to this's data, which I don't have to put this in front of. But in line 5, it will be the same as saying this hyphen greater data square brackets I is equal to A dot data, because remember, this is a pointer. So if I was going to use this, I could do that. But since I'm doing this locally, the compiler realizes that that data that I'm talking about is my own local one. So I can just say in line 5, data square brackets I equals A dot data square brackets I. So I can use A as a reference, and I can dereference things in its data that way. Once I've got this copy constructor and the constructor that's in the previous slide, you can see that I can do these declarations. A parentheses 10, which is going to give me an array of length 10. B parentheses 20 gives me an array of length 20. I can make a copy construction here in line C. I can use the curly braces on copy construction. C is going to be a copy of B. So whatever was in B, C is a full copy. In line 11, looks like an assignment at declaration time. It is not. It is a copy construction. That is some more syntactic sugar that is handled by the compiler. So I say array D is equal to B. I'm declaring D and at the same time setting it equal to B. That actually calls the copy constructor. All right? And then A equals C, I can do that, but this is going to give me shallow copy land. Remember, I talked about this member-wise copy. If I set A equal to C, it says A's length is C's length. A's data is equal to C's data. And since data is just a pointer, I've got two objects now pointing to the same memory block. So that's what's going on in this thing here. All right. I think I'm just about out of time here. How many slides do I have left? That's going to get me to the edge of that. No. All right. I'll do another couple minutes here, and then we're going to get out. So this is looking at the complexity of copying. Hopefully, you would think that this isn't going to be longer than linear. I've got n things to copy over there. That should take me no more than n time. And this is just a copy constructor that runs through and does those things in there. So I can look at this as big O of n in the best case, worst case, and average case, because I've got to have that for loop, and that for loop is always going to do the 1 plus 1 plus 2n work, and then everything inside it is going to be some constant amount of work that happens n times. So this ends up a big O of n across the board. As you start working on this, you say, well, I've got to have a copy constructor, and if I want to do this because I've got dynamic memory, I've got to do an equal sign. I've got to have an operator equals. They're doing the same thing, except the copy constructor does it on a new one, and the operator equals does it on an old one. So what if I was to just sort of make that class, that code common? And you see that's done here in lines 1 through 9. We've written this copy from function. So that copies my data from some other array. I can use that inside of my copy constructor here at line 11, and I can also use that inside of my operator equals here starting at line 15. So both of them make a call to copy from the constructor, and here at line 17 in the operator equals, those both call the same code that makes sure we've got enough space in data, has our length set properly, and then makes our own deep copy of whatever was in other. However, what I have to do here when I do this is make sure that I don't assign myself to myself, because the first step in copy from is delete square brackets data. I'm going to make sure that I've gotten rid of my data so that I can make a new copy from other. So I'm going to get rid of what I've got and then make a new one and put it in there. So that's what's going on there. However, if I set A equal to A, I would hope that A has A in it. If the first step of copying is deleting all my data, if I set A equal to A, the first thing I do is delete all my data. So setting A equal to A now sets A equal to nothing. Not a good look. So that's what this idiot check here is in line 16. It says, if this does not equal the address of other, because this is the pointer to the current object, and the address of other is the pointer to the other object. If those two things are pointing at the same thing, then obviously we don't need to do anything in operator equals. We're setting A equal to A, so we just return out of this. So that's what's known as the idiot check. There's a way to get around this, and we use this, and we do this, we call this the copy swap method. So the best way to do this is what's called the copy swap method. And in the copy swap method, what we're going to do is make sure we put all of that work back into the copy constructor. So here's our copy constructor as we saw it before we started putting things into copy from. But now during operator equals, we're going to use this code, reuse this code here in line 11 to say array temp other calls the copy constructor. So now temp has this done for it. So that's where the copying actually happens. Then I swap temp with this. I take temp's data, I take temp's length and put them in this, and then I can return a dereference to this. So I make a copy here and I swap it with mine. What that does is whatever I had before the operator equals is now inside of temp. Whatever I had before the equals is inside of temp. So when temp goes out of scope and gets destructed, it takes what I used to have. And the copy that I made of other in temp, I get to keep. That's what copy swap is. And that's where I'm pulling the end of the hour. We'll have to get some lunch and catch up with some of this stuff on the other side.